Hello, everyone. Thank you for having us. So I'm Michael. I'm giving the first part of the talk that Milica planned for this evening. And we're going to talk about shifts and other vices of human-computer dialogues. Okay, let me quickly figure out the controls. All right. So Hofstadter and Sander equate the questions, how many languages do you speak and how many languages can you have an everyday conversation in? And this kind of equation is pointing to the fact that natural language has evolved to facilitate communication. This is its main purpose. And what's important for us as researchers is that dialogue is a prime interactive natural language processing task. Dialogue is also a prime machine learning task to study distributional shifts. And this is what this session is about. Dialogue has many properties that decide whether or not a conversation is actually good. And a dialogue system naturally needs to be able to have good conversations. So that means that a system needs to be able to understand the user. It means that a system needs to handle an entire variety of topics and need to be able to talk about large and expanding domains. It means that systems need to understand emotions and sentiment. And they need to be able to conduct the conversation beyond simple question answering, which means that they need to have some ability to keep track of the history and to do some planning. Systems should respond in a human-like manner. That also means that they should respond sensibly, intelligently, and fluently. Systems should also provide personalized outputs because every user is different and every session, every dialogue is different. And there are many more such important properties. Now, why is dialogue so hard? Turing poses dialogue as a core AI problem, and the famous Turing test states that if a machine can converse like a human and hence trick humans into believing it is human as well, then it passes the test. So dialogue is hard because there is an infinite amount of possible trajectories of system and user turns. And we can always think of a dialogue that was never produced before, even if we have already seen a million different dialogues. Dialogue can also be viewed as an AI complete problem, which essentially means that we as researchers still have a long way to go to find methods that achieve human-like performance. Now, why do we need machine learning for dialogue? Well, we cannot solve dialogue using rules alone or simply using rules. And shifts are one of the main reasons for that. Shifts naturally occur in dialogue. It's just part of its nature. There can be a change of environment. Like in our case, we can go from a noise-free lab where we develop methods to the noisy street where we try to use those methods. There can be a change of domain. We might have trained something on the restaurant domain and then encounter the flight booking domain. There can be a change of users. We can go from simulated to real users, from experts to novices, from old customers to from young customers to old customers, from patient to impatient people, from polite to rude conversations. There can be a change of language, and there are many other shifts imaginable. The three main aspects when we talk about machine learning for dialogue modeling are data, the models themselves, and predictions. Obviously, we use dialogues as data to learn from. Those dialogues are typically annotated on the level of utterance or turns with semantic concepts. They are also annotated sometimes with user feedback. For the models, we can decide whether to use unsupervised learning or supervised learning. And what's also especially important in dialogue is reinforcement learning, which is, for instance, used for policy and decision making. For the predictions, we are interested in what did the user mean? what to say back to the user, and how to formulate this response to the user. Machines learn very differently than humans. With human learning, we can easily learn from single examples. We also tend to learn from noisy inputs and from correlated inputs. Most of the time, we learn in some form of unsupervised manner and even with delayed supervision. In contrast to that, in machine learning, we typically require IID data that is identically and independently distributed. And the cartoon on the right here is an ironic view on today's mantra of no data like more data. State-of-the-art models are trained with billions of examples, so they are very data hungry. And typically, the more data we have, the better the model will perform. There's also no free lunch. If an algorithm performs well on a certain class of problems, it pays for that performance by lower performance on the set of all other imaginable problems. Or simply put, there is no universal solution to all our machine learning problems. All right, what kind of dialogues are there? So dialogues are fulfilling different functions. We essentially divide dialogues into two types when we talk about modeling them. They are chit-chat or social dialogues. Here's an example. The system starts with, "How are you today?" The user responds, "Frustrated. We had to postpone our waiting yet again." "Oh dear, I'm sorry to hear that." What the social dialogues do is they typically don't model a particular goal. They allow the conversation to span over a huge number of topics and impose no restriction on the vocabulary. Task-oriented dialogues are very different. Here's an example. The user starts with, "Can you book me a PCR test? Do you have a high temperature? No, but I have lost my sense of smell. Okay, the next available appointment is on Wednesday at 3 p.m. So this is an example. It shows you that task-oriented dialogues, they typically have a goal or a number of goals to fulfill. That also means that they have a well-defined scope of conversation. When it comes to task-oriented dialogues, they require two fundamental conversational abilities. If you look at this figure here, then the circle in the center is the current turn we're in. The system has to be able to track information from the past. So this is something that the tracking module does, or the dialog state tracker. But coming from the current turn, we also need to be able to do some planning until the end of the dialog. And this planning is done by what's called the policy. For task-oriented dialogue modeling, we typically take a modular approach. And what you see here is the full pipeline. So this is including speech processing. We have we might have a speech recognizer at the beginning of the pipeline, which produces text hypotheses of what the user says. A belief tracker or a state tracker then needs to identify, given previous information from the current dialogue, what the user has said and what the user's goal is. A belief is then forwarded to the dialog manager, which contains the policy. This policy is trained using a reward function to pick the best possible action. It will forward an action to an action prediction to the natural language generator, which then outputs a text or text distribution so that the text-to-speech synthesizer can then provide the answer to the user. And as you can see here from this figure, all of those modules is underlying an ontology. An ontology essentially defines what the system can converse about. As is typical for modular systems, we also have the problem of error propagation in dialogue modeling. So if you make an error in your speech recognizing module, in the very worst case, this error might be propagated until the very end of the pipeline, accumulating more errors and thus dramatically reducing your performance. So what we need to do is to model alternatives. And this is where uncertainty modeling comes into play. So in this example here, in this pipeline, if we started having a state tracker here, we would now have a belief tracker. Belief tracker is basically modeling or predicting a distribution over all possible states and not just predicting one single state. So here we would forward a belief state rather than a dialog state. The policy, in turn, would forward a distribution over possible actions rather than a single action prediction. And the natural language generator would do the same. It would forward a text distribution rather than a single prediction. Statistical dialog modeling has already quite a long history. One of the earliest models for dialog were Markov decision processes. These models were optimized in interaction with a simulated user. These were succeeded by a partially observable Markov decision process, where the dialog state is modeled as an unobservable variable. With Bayesian networks for dialog state tracking, the dialog state becomes decomposed, and we learn transitions and observation probabilities. Gaussian processes for dialog policy optimization significantly reduce the amount of interaction that is needed to optimize the policy. And nowadays we rely, like many other people too, on large pre-trained language models, which largely remove the need for careful feature engineering. All right, let's now look at a particular task where shifts pose a considerable challenge, and that is dialog state tracking. The role of the dialog state tracker is to remember what has been said so far in the dialogue. This often means tracking only the user goal at every dialogue turn. So we need to keep track of the domains, slots, and corresponding values relating to entities in the database. So domains could be things like, could be topics like restaurant, hotel, plane, booking, and so on. Slots are concepts belonging to those topics. It could be the name of a restaurant, the type, the location, the price. And corresponding values are instantiations of those concepts. For instance, cheap, expensive, north, south, and so on. Dialog state trackers are typically evaluated using joint goal accuracy, which is computed of, it's the accuracy of all slots at every turn averaged across dialog. Now, what happens when we change the names of entities of the test set? And Kian and colleagues did a test like this this year, and the table shows that essentially for many such methods, the performance drops drastically. It basically breaks the system. And I mean, there is no useful prediction anymore. There are two critical properties that are required to handle shifts in dialog state tracking, and that's what we want to talk about. The first property is what's called value independence. I'm going to talk about that next. And the other one is uncertainty modeling, which then will be talked about by Nurul. Here is a concrete example of how shifts occur in dialog state tracking. Data-driven state trackers require an ontology, which cover the domains, slots, and values, and the database, which cover the entities that can be described. We also require the dialogues themselves and the labels for those. And we use this data to build systems. Now, what happens when we add new entities that have new values and try to do inference? So it's imaginable that if you have a restaurant recommender, that there is a new restaurant opening in town that you want to cover. Or maybe the train has a new stop, or a new payment method is introduced. This is something that we addressed in a work called Trippy, which stands for Triple Copy Strategy, for value-independent neural dialog state tracking. So we looked at the value independence property in particular, which is the ability to track values that are not in the ontology. So exactly the case as I just described. These are also called out-of-ontology values. Trippy is utilizing contextual word embeddings to do dialog state tracking. And the dialog state is constructed using span prediction, but it also deploys a triple copy mechanism. Here is an example of a dialog as Trippy would process it. The user starts with, I'm looking for an expensive restaurant in the center of town. Expensive and center are both values that are explicitly mentioned in the context, and therefore they can be extracted via span prediction. There are 33 restaurants. Would you like to narrow your search by type of food? I do not care about food, surprise me. So this I do not care is a special case where we simply predict that the user does not care about a particular value for a slot. Fitzbilly's restaurant serves British food. Would you like to hear about any others? That sounds fine. Can you book it, please, and get me the reference number? Here, the user did not explicitly mention the restaurant name. Instead, the system was mentioning a restaurant, and the user referred to it in a positive way. In this case, we have to resort to one of the copy mechanisms, which is the inform memory. Sure, what day and time would you like and how many people? I would like a table for 5 at 11:30 on Tuesday, so no problem here. We can use span prediction for all 3 of those values. And then it continues. Okay, the booking was successful. Is there anything else I can help you with? I'm also looking for a place to stay. It needs free Wi-Fi and be in the same area as the restaurant. Now, free Wi-Fi is a value that belongs to a Boolean slot. So here in this case, we only have to predict a true or a false value for that slot. Same area as the restaurant is a very interesting case because here the user refers to a value that has previously been filled into another slot. So we effectively have to do coreference resolution, which we can do with another copy mechanism in Trippy, where we can identify a slot that has been referred to and then simply copy the value from several turns before. But now I will walk you through the model design step by step and explain all those things. For each turn, the dialog context needs to be encoded first, and this is done by the context encoder here. The encoder takes as input the current user utterance, the preceding system utterance, and the entire dialog history. The output of the encoder is one sequence representation here and a sequence of token representations, and those are used for to solve several subtasks. The slot gates here on the left predict for each slot whether a slot value is present in the input or not. The gates also predict which of those copy mechanisms is best suited to fill a slot. If it decides for span prediction, then the span prediction output is used. That would be here on the right-hand side. If it decides for inform, then it uses the inform memory. If it decides for refer, it will predict which slot is being referred to by the current slot. And that's again done with a different prediction head here. And lastly, Boolean slots have their own separate slot gate, but that works in the very much the same way. Okay, the first copy mechanism is span prediction. Here we predict for each token the probability to either be a start or end position of a span. And in order to identify a span of relevance, we simply take the positions with the highest probability. So we take the start position with highest probability, end position with highest probability, and everything in between would be the predicted span. The second copy mechanism is from the inform memory. So we keep a memory of what has been mentioned by the system during the course of a conversation. That's called the inform memory. The model checks for the presence of a slot that the system has informed about. And if there is no span prediction possible, for instance, because the user did not explicitly state the value him or herself, then the value stored in the inform memory is copied instead. And this idea is related to grounding. If you want to understand grounding, then just think about a conversation between a pilot and the flight control. They need to share a common ground in order to communicate properly with each other. The third copy mechanism is used to do coreference resolution. For that, the system keeps a dialog state memory. For each slot that the user mentions, the slot gate predicts if it is referred, if it refers to a slot that has been previously filled. So it simply does a binary classification whether or not there is a referral happening. If there is a referral happening, then a separate classification head will identify the slot that has been referred to. If the referred slot has been identified, we can simply copy the previously mentioned value to the current slot. All right. We evaluated Trippy on a range of data sets, most importantly on the Multivoice data set. Multivoice is a multi-domain task-oriented dialog data set. It has been collected in a Wizard of Oz fashion, and then has been labeled with domains, slots, values, and intents. It's a moderately sized data set with over 8,000 dialogues. It covers 7 domains and has about 4,500 values. At the time of publishing this work, Trippy achieved the state-of-the-art performance compared to other recent methods. Since then, of course, there has been new works being published. It is, however, nice to see that many of the state-of-the-art methods build upon Trippy. So we're quite happy that our work is being picked up and people show interest in what we're doing. What I mentioned before is that we were particularly interested in the value independence property. And in order to test this, we did an extreme experiment that's similar to what Kyan et al. Did. For that, we replaced all the values in the original Multivoice test set with previously unseen values. So that those are values that have never occurred in the training set. The underlined slots here are slots with at least one out of ontology value. And the average out of ontology, out of vocabulary rate is 90%. So this is a very high number of out of ontology values. And what you can essentially see in this figure is that the performance is largely stable, except for very few exceptions, which shows that the model definitely has this property of being value independent. All right, this is the point where I hand over to Nurul for the second part of the talk.
Okay, so the second thing that we try to tackle for handling shifts in dialogue state is how to model uncertainty in the prediction. So we see, as Michael has presented, neural dialogue state tracker nowadays have achieved impressive results given how it started. So the best trackers today are have joint goal accuracy of about 60%. So this means they are still wrong 40% of the time. Now, the problem is that on those predictions where they are wrong, they are fully confident in that prediction, even though they are wrong. So they don't have a nicely calibrated uncertainty modeling. Furthermore, we also see that if we see state-of-the-art models published today, they typically are evaluated in terms of joint goal accuracy in isolation. So we haven't looked yet at its downstream effect on the dialogue system or dialogue policy. And this is another problem is that they nowadays focus only on user goal. So there are still some other components that are necessary for the policy that the dialog system is not providing. So what are the solutions? What we try to do in this work is to track full dialog state based on which the policy can make a decision. I'll talk about this in more detail later. We also would like to incorporate additional uncertainty measures and to examine the downstream effect of uncertainty on policy optimization. Most importantly, we would like to examine the shift that happens when we move from interacting in a simulated environment versus interacting to actual human users. So what goes in the dialog state? So far, we've talked about these concepts in the ontology that described the user goal. But actually, Young and colleague in 2007 have posited that a dialog state needs to incorporate three things to, to be Markov in a full dialog system. So in addition to the goal of the user, it also needs representation of the dialog context, as well as predicted action of the user. So we call our model SetSumbity. This is developed based on the slot utterance matching belief state tracker, or SUMBITI in short, proposed by Lee and colleague in 2019. The model takes as input descriptions of slot and values, and then measures similarity using multi-head attention and set pooler. And in our SetSumbity model, we track four things. The first is the dialog context, and then the user goal, the user action, as well as the current active domain, because we deal with multi-domain dialog setting. So let me take you through the model step by step. So the model takes as input current user utterance, latest system utterance using a fine-tuned language models, for in this case, Roberta. We also take a description of domain slot pairs. At each turn, we encode the utterances only once. The slot utterance matching and the context tracking components are utilized once for each domain slot pair. And the model further requires a predefined set of plausible value candidates for each domain slot pair. So they're both encoded with a language model as well. Further, we use the set pooler once for each domain slot pair and once for each value candidate. And the set pooler that we use here shares the same parameter. And then using these, SetSumbity outputs a belief state distribution for the relevant domain slot pair. And this is what constitutes the user goal. In addition, we also here predict a distribution over general actions such as goodbye or greetings. We also predict the probability of a user request, whether the user requests the domain slot pair. And it also predicts the current active domain. So how do we model the uncertainty estimations? The predictions from ensembles are often more accurate and better calibrated than those from a single model. So how do we create the ensemble? One thing we could do is to randomly split our training data into n subsets, in this case 3, and then train a model from each of those subsets, and then combine them into one ensemble. And we see that this is actually pretty useful in achieving a better calibrated uncertainty estimation. If we compare a single SUMBITI model with an ensemble of SUMBITIs, In this case, blue is a single model and green is an ensemble of 3 models. We see that for the dialogue that we see on the left, so the users say, "Hi, I'm looking for a hotel by the name of Acorn Guest House." The system answered, "Sure, what would you like to know about it?" "I would like to know if it is available for 8 people for 4 nights starting Saturday." If we ask the tracker what's the value for the day slot, the single model puts full confidence on that slot not being mentioned yet in the dialogue. And the ensemble model, even though the majority probability mass is on non-mention as well, it actually also puts some of it on the correct value, which is Saturday. So even though it's wrong, it's not fully confident on that wrong prediction, unlike the single model. So with Ensemble, given an ambiguous user input, such as I want something not too expensive, but not cheap, we can, based on the predictions of each of the model in the ensemble, we can measure the data uncertainty, the knowledge uncertainty, and the total uncertainty. So the entropy of the predictive posterior is an estimate of the total uncertainty. And ensembles allows decomposing total uncertainty into data and knowledge uncertainty by considering measures of ensemble diversity. Data uncertainty is the uncertainty due to noise or ambiguity in the data, and knowledge uncertainty is uncertainty due to a lack of knowledge of the model about the test data. So for example, if the test data is pretty different from the training data, anomalous or atypical. Thus, measures of ensemble diversity yield estimates of knowledge uncertainty. These quantities are obtained via mutual information between predictions and model parameters, as can be seen here. So while ensembles provide improved predictive performance and a rich set of uncertainty measures, they're unfortunately unpractical for real deployment in dialogue systems because their inference time and the computational cost is quite high. So methods to distill ensembles can be really beneficial for dialogue system. In particular, END or ensemble distillation proposed by Hinton in 2015, for example, can be used that compress an ensemble into a single student model that allows us to estimate the total uncertainty. One drawback is though that we are not able to obtain the knowledge uncertainty because it is lost in the process. On the other hand, END squared or ensemble distribution distillation provides a single model which also can estimate knowledge uncertainty. So then we also, as mentioned, we also would like to see the effect of the tracker on policy optimization setup. So we do so using a Conflab 2 toolkit on a multi-domain environment using the Multivoice data. So our system consists of the proposed SetSumbity tracker, dialog policy optimized with PPO, and a template-based natural language generator. And then the dialog policy interacts with user simulator or in a simulated environment to optimize the policy. The simulated user make use of value variations to introduce noise and uncertainty in the dialogue. So we randomly replace values such as expensive with a synonym such as high class. The confidence scores replaces indicators in the policy model feature space, whilst knowledge and total uncertainty measures are added as extra features. First, let's look at the performance of the state tracker on its own. We look at joint goal accuracy as other works, but in this case, we are also interested in expected calibration error, or ECE, and this measures the difference between the confidence and accuracy of a model. We see that here, even though in terms of joint goal accuracy, the differences are not too apparent, but in terms of ECE, we can really see a difference between a single model and a model that uses ensemble or distilled ensemble. Ensemble here, we treat it as an upper bound performance for the calibration of the model. So if we plot the confidence against the joint goal accuracy, we can see that the ensemble models are better calibrated. Their confidence on the x-axis aligns more with the joint goal accuracy on the y-axis. So the single model, SetSumbity in a blue solid line, we can see that it fits more poorly to the diagonal line that shows perfect calibration. And the other model with the dot and dashed line is closer to that, so it's better calibrated. So how does this effect shift from simulated environment to human user? We actually do this through Amazon Mechanical Turk. We devise a platform that lets worker interact with our system using the dialog crowd platform. And in total, we collected approximately 550 dialogues for each of the different systems. And in total, there were 380 workers that took part in these experiments. So quite a wide distributions of users. And what we see here is that SetSumbity, which only uses confidence which only give the confidence measure to the policy, achieve lower success rate in either environments. And model that uses uncertainty measure, a better calibrated uncertainty measure, performs better in simulated user environment as well as human trial. So it shows that this actually makes the policy more robust to noise or uncertainty or distributional shift in the data. So it shows that it actually has an effect on the downstream performance of the dialog system. So what does this show us? What's the benefit of modeling uncertainty? END squared SetSumbity system outperforms all other versions of the system in human trial. Well-calibrated uncertainty estimates assist in training a more robust dialog policy model. Dialog belief and state tracking models should not only be evaluated in isolation, so we need to see its effect on the dialog system. Both the accuracy and calibration of a dialog belief tracker are important. So to sum up, adaptation is a key milestone towards dealing with conversational shift for dialogue system, and the road to adaptation is multifaceted. And conversational agents will become more ubiquitous in the future. We already see this trend happening. If we look back a few years ago as to now, they are more integrated into our technologies. So, and they will do important things such as providing information to us, teach us things we don't know, and maybe even give advice to us. They could be virtual, embodied, or multimodal, and it is human nature to communicate via language, and the machines must embrace it. So we'd like to thank the entire group, Nurul Lubis, myself, and Michael Heck. We're the postdocs. And of course, the PhD students in the lab, Karel van Niekerk, whose work I just presented, Christian Geishauser, Shenzhen Lin, Shutong Feng, and Renato Vukovic. And of course, Professor Gasic, who unfortunately couldn't be here today. We'd also like to thank our funders, ERC, the European Research Council, Alexander von Humboldt from Sofia Kovalevska, and also Google Cloud for providing compute. Thanks.
Hey, thanks for a great talk. So now's the time to ask any questions you may want to ask from the audience. I'll just start with a couple of questions of my own. So in your last bit about uncertainty estimation, so you, if you can just flip to the results slide, you can just see the numbers, right? So I'm really curious to know why standard ensemble distillation worked better on simulated users, and ensemble distribution distillation worked a little better on the actual human trial. You know, on the human trial.
Right. So yeah, we also discussed this point with the group, and we believe, so if we look at the difference of the performance in the simulated environment, it's quite small, it's less than 1%, whereas this gap is higher on the human trial. And I think that goes back to the diversity or the the amount of noise that's present in each of those environments. So the simulated user uses a template-based NLG, meaning that for certain actions, it just has a template which then the values are filled into the template. So there's not that much variation in the user input. Whereas if we think about a human user, just some worker on mTurk, they could say one thing so many different ways. And that's where I think robustness or from the uncertainty is more beneficial for the policy. So yeah, that's why the numbers is this way.
Okay. Yeah, that I think that makes a lot of sense. Is that we just see more anomalies in the human data, and the knowledge uncertainty helps us pick up on that. Okay, cool. Where do you see this going in the future? What's the next step?
Yeah, I mean, so I think interactive evaluation is really becoming more important for dialogue systems. So now many of the evaluations we do are offline based on data. So to push that state of the art, it's yeah, that's where we are focusing right now. But truly, if we build dialogue system, the main goal is to have it interact with people. And when we put this system into real interaction with humans, things are just more unexpected, and we see what problems there are, and then we come up with new interesting solutions, I guess.
Cool. Yeah. Does anybody else have any questions for our speakers?
I see there is a question in the chat.
There's questions in the chat, which I didn't see. There's questions about sharing of the videos. Yes, so this is all recorded, and we'll post this on the internet page. Sorry, on the Shift challenge page a bit later. After this will be recorded, we'll post this on the Yandex YouTube and on the Shift challenge page, and we might even link it on GitHub just so everybody has access to this, and we'll tweet about it. So yeah, people who are, who are missing out for various reasons will be able to still see this. Or am I, sorry, or are you seeing all the, sorry, maybe I'm not seeing all the questions. Are you seeing the questions? Are there other questions other than about the videos, Ludmila?
Yes, I see one question which is probably posted privately for some reason.
Can you? Right, I think you're on the other on the other actual official account. Can you just ask that question?
There is a question: what is the core difference between Trippy and Poly AI?
Between the other one, I did not hear. Sorry.
Let me just send it to the chat for convenience. 1 second, so that I just copy the question to the chat.
Poly AI.
Yeah, Poly AI.
At this point, I cannot answer this question because I don't know enough about Poly AI, but I'm happy to give a response to that in some other way if possible.
So I know that Poly AI is the startup that does.
Yes. Yeah.
Maybe they can come up with a new state tracker. Yeah.
Yeah, but I'm unfortunately not familiar with the details of how they are performing the state tracking task. So I cannot give an answer to this at this point.
Any other questions going around from anyone? You don't have to be shy. Right. Well, anyways, I guess that's it for this bit. In 15 minutes, we should have Rowan McAllister from Toyota Research coming on to give a talk on uncertainty and robustness in autonomous vehicle planning. So stay tuned for that. That should happen in another 15 minutes. And yeah, during this time, we can either just chat away here or wait. Oh, sorry. There was a question follow-up about Poly AI, the state of AI 2020. So
Convert.
All right, so if this is about intent detection, I don't know if this is about intent detection, but it's something that the current version of Trippy does not do yet. We are, however, working on versions that are incorporating intent as well, because it's one of the important parts to make things work in a complete pipeline. Nurul pointed out the problem that we often test things in isolation. And if we are using user simulators, so real users, then the state tracker needs to provide more than just predictions of what the user meant with regards to values. So we have not incorporated that when we published the original Trippy because it was not a requirement. But we're doing this now so that we can run the full pipeline. But I don't know if that is answering the question.
I guess they don't use copy mechanisms the way Trippy does. Yeah.
Yeah, I mean, one distinctive property of Trippy is those the usage of those 3 copy mechanisms. We do use span prediction, which obviously we're not the first to do that. In fact, we took BERT DST as a starting point when we started working with dialog state tracking, and then we built upon the idea of span prediction of extractive methods by adding those various copy mechanisms to it. And that is something that wasn't there before. There are different methods to do coreference resolution, for instance, but not in this particular way where we are maintaining a memory and then identify cases of coreference and doing a copy operation. And more importantly, also, it is rather new to incorporate the information that the system provides about what it talks about. So this is an assumption that we incorporated into the model, that the system knows what it is talking about. So we can as well utilize that to use different forms of prediction when we do state tracking. And this, using those 3 copy mechanisms, rather than just, for instance, span prediction or just like pick list based prediction, that helps us to be value independent. So that's a distinctive feature. And I think that's not just a difference to what PolyAI does, but what other methods do in general.
But do you think that intent detection is still necessary? Or do you reckon you've bypassed the need for it?
Yeah. Maybe you can say something to it because you're working with the pipeline. So
yeah, so I think it depends on which level of abstraction the system works in. So so far in the talk we focus on end-to-end dialogue system, where we move step by step from one abstraction to the next, like from speech to text, and then to semantic representation, and then back to speech. In that case, intent detection is certainly necessary because there is some modules in the pipeline that needs input in that semantic level abstraction, which intent detection does. But there are also end-to-end models that works just from sequence of words straight to sequence of words. Yeah, and there is a trade-off, of course. Like if you need these different level of abstractions, you need more labels to train, and you need separate modules which could propagate errors. On the other hand, if you just do sequence to sequence end-to-end model, you could bypass that, but of course then the model itself becomes less transparent and more of a black box, and it's harder to troubleshoot issues. Yeah, so there is, I think, still a necessity for intent detection as far as dialogue modeling goes.
Makes sense, thank you.
There's one more question. So there's are there cases of multiple co-references from past contexts or utterances in a current conversation? If yes, how do you disambiguate?
Okay, let me just read it again. So I assume this is referring to like multi-hop cases where you have a co-reference and then you might refer to this again in 2 steps. This would actually not be, yeah, I don't think this would be a problem actually. It might be an issue if it happens within a single turn, which is hard to imagine right now. But if it happens across multiple turns, then you would have updated your dialog state by resolving a coreference, and then you could do the next coreference. So I don't see that there would be an issue. Does that answer the question?
I think they were asking about single step.
Maybe multiple slots.
So the comment is yes for multi-hops, but single hop, multiple slots. How do you help user converge?
I guess Trippy makes these predictions independently for
Yeah.
each of the slots, right?
Yeah.
So in ideally, then for both of those slots, the refer prediction should be turned on, and they would pick the appropriate respective coreference slots.
Yeah, that's correct. So if multiple slots refer to multiple other slots, then those are treated as individual cases, and they would just be resolved independently. All right, good.
All right, let's just all take a 5-minute break, and then we'll come back at on the hour sharp for our next keynote speaker, Rowan McAllister. Thanks.